Okay, now that we've looked at complex numbers, it's time to look at functions of a complex variable. So let's see what those things are doing. Functions of a complex variable. Well, basically, just like we can map real numbers to real numbers, of course, we can also map complex numbers to complex numbers. So the underlying definition shouldn't change that much. But because C is two-dimensional when we think of it from a real numbers point of view, a complex function basically has two real inputs and two real outputs. And that means that whenever we connect back to real numbers, we will need some multivariable reasoning, which is especially true when we're visualizing. At the same time, this is also the reason why we'll usually work with the complex numbers themselves, because a lot of the computations, you just have one input variable that is called z, you'll have an output variable w, and just working with that single symbol is a whole lot easier than always puzzling the real and imaginary parts apart. Okay, the other thing, and this is now definitely new, is it becomes interesting to consider the images of subsets of the plane that are substituted into a complex function. And basically that's because if you consider the function as a transformation, and we'll talk about that separately later on in this presentation, we get a very visual interpretation of those functions, and that is rather nice. And it is an early stage to visualizing things like fluid flows, for example. Okay, so let's just start with the definition, and the definition is that a function of a complex variable is a rule that assigns to each number z in a domain D of complex numbers a unique complex number w, which will also be denoted w equals f of z. Now, if you drop all the references to complex variables here, you have exactly the definition from calculus of a function of a real variable or of a function, and so that shouldn't be anything new. But now we've got a couple of conventions. If the domain is not explicitly stated, we assume that the domain is a set of all numbers for which the rule can be applied. That's basically also a calculus convention, but now notice that because we've got the complex numbers available, the domain is larger than just a subset of the real line, potentially. The particular domain, then, just as in calculus, is called the natural domain of the function. And note that if our input z is x plus iy, and if we call w u plus iv, then f of x plus iy is f of z, which is w, which is u plus iv, which therefore, because this is a complex number, is u of r, because these things now depend on x and y, is u of x and y plus iv of x and y. So that means every complex function really can be considered as a pair of real functions u and v of two real variables. And even though that requires more bookkeeping, this switching back and forth between these two viewpoints can have some rather useful consequences, so we want to get used to doing that. We will sometimes refer to u and v as the real and imaginary parts of the complex function f, and we will usually use w for f of z, and we will say that w is equal to u plus iv. So even though there is no natural rule that says that the real part is always u and the imaginary part is always v, it usually will be the case, and that will allow us to proceed a bit more quickly in certain things because we don't have to keep telling people what the real part and what the imaginary part is. Okay, let's take a look at some examples, and the examples are couched in the instructions. Well, find the real and imaginary parts of a function, say f of z equals 1 over z. That's a function that, of course, we know rather well on the real line. It's defined for z not equal 0, because you can also divide by any non-zero complex number, of course. And so now if we want to puzzle it apart from the complex point of view, we know that f of z is 1 over z, which is 1 over x plus iy, and we can now expand with a conjugate to get, so we multiply numerator and denominator by x minus iy to get x minus iy over x squared plus y squared. And that's just x over x squared plus y squared minus iy over x squared plus y squared. And so that means that the real part is u of xy equals x over x squared plus y squared, and the imaginary part is negative y over x squared plus y squared. We can also look at the real and imaginary parts of the familiar function z squared, and f of z equals z squared would be x plus iy quantity squared, and now we just multiply that out. we get x squared plus 2xiy plus iy quantity squared. And if we now sort that out, well, iy quantity squared is negative y squared, so we get x squared minus y squared, and then we've got this I here, which gives us I times 2xy. And so that means the real part is u of xy equals x squared minus y squared, and the imaginary part is v of xy equals 2xy. Okay, we can also define complex numbers via polar coordinates, via r and theta. And so, for example, if we take a z equals r e to the I theta, where r is greater than 0 and theta is between negative pi and pi, where pi is inclusive and negative pi is exclusive, we can define z to the 1/2, the square root function, to be the square root of r times e to the I theta over 2, and that notation makes sense because we know if we were to square that, we would get e to the I theta and we would get r, so we would get z back. We have to be a bit careful here because if you go once fully around the circle, starting at, well, let's go counterclockwise. Start at pi and go clockwise around the circle, around the origin, and you realize your argument ends up being negative pi on the other side, and that can have certain problems for the continuity of these kinds of functions, and we'll have to talk about that in more detail once we investigate things like logarithms and so on. Actually, for the square root function, there is not a problem there in terms of continuity. All right, well, we move on to functions as transformations, and so we want to talk about complex functions that map subsets of the plane to subsets of the plane. And well, let's first think about the real line again. On the real line, we really haven't talked about that much. In fact, rarely at all, because there really aren't that many interesting subsets of the real line. Just about everything in calculus is defined on an interval, and it should be. Now, there are some interesting subsets, interesting in often a pathological sense, actually, and to fully appreciate those subsets, we would need an advanced class in analysis, so we'll leave that be. So for the purposes of this class, really there isn't that much interesting stuff going on the real line. But there are all sorts of interesting subsets on the plane, because now that we've got that second dimension, we can do geometry there, right? I mean, there's all sorts of nice geometric figures in the plane, so the interesting subsets can be curves as well as two-dimensional figures. And to visualize what a complex function does to these kinds of sets is a very good exercise in combining visualization with algebra, because of course an algebraic expression is how the function is typically given, and then we translate that into what's happening to the pictures. Plus, as I said, in terms of applications, these kinds of things can help to visualize fluid flows if, say, we pretend that the input is what a glob of fluid looks like at the start of the observation, and F maps every particle to its position after some time has passed. Okay, so let's visualize the function f of z equals z squared, and let's first just think about angles. And well, what does z squared do? It doubles every angle. So if I take that function and I take this angle here, then the function z squared takes that angle. And of course, it doesn't go through that smooth transition, but that smooth transition is quite helpful to just get a dynamic viewpoint of the whole thing. And what it does is it turns that angle into double what it was before. Well, that's something that we knew because, of course, e to the I theta quantity squared is e to the I 2 theta. And because we just looked at the angle, we didn't really see anything in terms of how things are getting stretched along this leg of the angle here. But now if we're looking at regions, let's start with something like a circle here, and let's see what z squared does to it. Well, as I slide that along, it seems like the circle gets bigger, but that's not quite all, because as we can see here, now that thing doesn't look like a circle anymore. And if we go all the way through this animation, we realize here we get something that is certainly not a circle anymore. I'm not even sure how closely it approximates a circle here. It still roughly looks like a circle with a little bump in it. And so that means that in certain ways we can say that functions, complex functions, take complex regions and deform them into new regions. And then again, this continuous transition in between is something that just helps with the visualization. It makes it prettier, and it makes us think a little bit more of things like fluids and so on. Okay, well, let's see. So the interesting thing now is that rather than just looking at animations, we can actually predict the effect of a function such as z squared on certain shapes. So for example, we can show that z squared maps the hyperbola 2xy equals c2 to the horizontal line v equals c2. Remember, v is the imaginary part of the output. How does that go? Well, recall that f of x plus iy with f of z equals z squared, that was x squared minus y squared plus I 2xy. Now, if you don't remember that, that's not a problem. Don't memorize it. Just go ahead and multiply that out and you'll get this back. I mean, there's no magic happening here. Now, if our input satisfied 2xy equals c2, then this is just a number here, right? So if xy are so that 2xy equals c2, then the imaginary part of our output is c2. It's stationary. So that means our output lies on the horizontal line v equals c2. And because the real part is x squared minus y squared, and because I can get enough combinations of values x and y on this hyperbola, we actually sweep out the whole horizontal line. And we can even visualize that by starting with the hyperbola, and as we square that, basically what happens is that the hyperbola bends around and straightens out more and more and more until it basically in the end becomes a straight line. Now you may ask yourself here, how did I generate these animations? Are these animations really true? Well, basically it's not that hard. I just took the curve originally here, and so that curve is z, and the intermediate stages are z to the first, which is the curve, z to the 1.01, z to the 1.02, z to the 1.03, and so on, which gives us more and more deformations that continuously take the input curve and ultimately turn it into the output curve z squared, which is right here. I even stopped that correctly. Okay, another example. Let's take a look at z squared again and show that it maps the region in the first quadrant that is between the axis and that hyperbola that we've talked about, 2xy equals c2, where c2 is supposed to be greater than 0, to the horizontal strip 0 smaller equal v. That should be a v here. Okay, we're back. Getting more and more proud of myself that I know how to use the pause button. Okay, that's a v now here. And basically we assume that c2 is greater or equal than 0, otherwise, of course, this part wouldn't make sense. Alright, so the argument is similar to the previous argument. We first note that c2 is greater or equal than 2, and greater or equal than 0. And so because f of x plus iy is x squared minus y squared plus I times 2xy, if 0 is smaller or equal than 2xy is smaller or equal than c2, and that is the case for this region, right, between the axis and the hyperbola 2xy equals c2, then we have that 0 is smaller or equal than the imaginary part, which is smaller or equal than c2. And moreover, because the real part is x squared minus y squared, again, we sweep out the whole region. And so visually, what that means is that we start with this region here, and the function takes that region and, of course, opens up the angle. And as we square the region, that's interesting to say, but we literally do square the region, we end up with this horizontal strip here. Okay, in terms of visualizing square roots, well, basically square roots are nothing but the square function in reverse. So for example, the square root function takes this horizontal strip and turns it back into the region between the axis and the hyperbola, as we had talked about previously, right there. And well, then we can also talk about functions such as f of z equals e to the z. And we want to show that that maps the vertical line x equals c1 to the circle around the origin of radius r equals e to the c1. Well, let's see. F of x plus iy is e to the x, e to the iy, e to the c1, e to the iy. And because y is arbitrary, well, e to the iy traces the full circle around the origin, and in fact, it does that infinitely many times, right? Because y is arbitrary, and this function repeats every 2 pi. And the circle's radius is e to the c1, which is this number right here. So that's how that works out. I don't have animations for those because I really haven't thought much about how I can do a continuous deformation of that really reflects what the exponential function does. We can also show that the exponential function takes horizontal lines and maps them to rays of the origin. So it takes y equals c2 and maps it to the ray theta equals c2. And that's again f of x plus iy is e to the x, e to the iy, e to the x, e to the I, c2. And because e to the x can now be any positive number, the image is the ray from the origin to infinity that comes off at an angle c2 of the x-axis, because this part here, of course, makes sure that everything is at that angle c2 of the x-axis. Okay, and consequently, that means that e to the z maps regular rectangles to polar rectangles, because, well, regular rectangles consist of horizontal and vertical line segments. Horizontal line segments are mapped to segments on rays of the origin, and vertical line segments are mapped to segments of circles. And so the result, as long as we've got the appropriate spacing and don't wrap around the origin multiple times and all that, that looks like a pie slice out of which the center was removed, and that's a polar rectangle. I don't have a dynamic visualization, but basically, if you have a rectangle that goes that has vertical sides y equals theta 1 and y equals theta 2, and has horizontal sides y equals theta 1 and y equals theta 2, and vertical sides x equals actually logarithm of r1 and x equals logarithm of r2, well, then what happens is the horizontal sides are being mapped to segments on a circle of radius r1 and r2, and the vertical sides are mapped there, and the horizontal sides are mapped to the connecting pieces on a ray at angle theta 1 or at angle theta 2, and so that means that those sides are becoming what we also call a polar rectangle. Okay, well, that's it for complex functions. You've seen that there's a good bit going on visually. There's also a good bit going on algebraically, and it's quite different from what we've been doing for real functions, because for real functions we always drew a graph that contained input on the x-axis and output on the y-axis. Notice that this is something we cannot do for complex functions at all, because with a two-dimensional input and a two-dimensional output, we would need to draw a four-dimensional graph, and that really is why these visualizations of what input regions go to what output regions are so important here. We can't draw the four-dimensional graph, but we can talk about how a complex function deforms input regions into output regions. Okay, with that, thanks a lot, and well, have some fun with the homework problems.